Hey everybody, Dr. A here, and in this video we're going to be providing some additional background information on how to handle distributed loading. In particular, we're going to be studying how do we find the location of the equivalent load due to a load distribution on a member. But before we get started, don't forget to hit like and subscribe and be on the lookout for other content like this. All right, let's get started now.
Okay, in this video, we are going to be extending our discussion from the previous few videos, and we're going to be talking about the location of the total equivalent force. So up until now, the past few videos, we've talked about computing a total equivalent force when you have some kind of distributed loading. Now what we're going to talk about is where is the equivalent force located along the length of the beam or the member that it's acting over. So we're going to write this sentence. We're going to say the location along the member that the total equivalent force is known as the centroid of the load distribution. Okay, so again, we're learning this new word called centroid, which is the location on the member's length that equivalent force, capital F, is located. Okay, so the question is, how do we compute that? So here's how we do that. We're going to say from equilibrium, we have the following. We'll say the sum of the moments about point O equals the sum of the total moment also about point O. Okay, so we're going to say where M sub T sub O is the moment due to the total equivalent load, capital F. So what we have to think about here, we have to think about equivalent systems, and equivalent systems is what we've been discussing, the past couple of days in some previous videos. We have a given system, and then we write it as an equivalent system. So we kind of have to think in terms of that. So let's look at an illustration. Let's say that we have an original system that looks kind of like this. Let's say that we have a member length here, and we have a W-axis here and an X-axis here, okay? And then let's say that we have this, somehow we have this distributed load W as a function of X, all right? And this is spread out over a total length of L, all right? And let's say that we have an equivalent system that looks kind of like this. We have the same member length L, okay? And we are going to have capital F here. And again, we know how to get F, right? We know how to get F. We'll make a little star here. F equals the integral from 0 to L. W is a function of X dx. Okay, so there's our equivalent system. So the question is, what is this distance right here? I'm going to call it X bar. Okay, I'm going to call that X bar. So I'm going to say X bar equals the location of the total equivalent load, F, and we can also sometimes call that X bar is the centroid of W as a function of X. Now, I forgot to put this on here, but we're going to put this as our origin right here. This is our origin point, the far left point. So that was pretty implied, but now you see it. So how do we kind of formulate this? How do we piece this together? Well, it all goes back to moment equilibrium right here. We said the sum of the moments about point O in the original system equal the sum of the moment about the moment about point O in the equivalent system. All right. So let's write that out then. Okay. Let's say that actually, you know what's interesting? You probably don't really need this summation right here. I mean, you can keep it there if you want, but I think you could erase that summation there if you wanted to. I don't think the book has it in there. It looks like the book does not include a summation there, but you could keep it there if you wanted to. It's not really going to change your problem. So I'll rewrite that here. We're going to say the sum of the moments about point O from the original system equals the total moment about point O in the equivalent system. Okay, so let's piece that together. Looking at the original system, what do we mean by the sum of the moments about point O in the original system? How do we kind of rationalize that with a distributed load? Well, here again, we need to think of it in an integral form, okay? Let's say that we have a little slice right here, a little slice, and let's call that slice, let's call it little df. That's a differential slice of w as a function of x, okay? So when you look at that differential slice df, that's teeny tiny. That's a infinitesimally small slice. So if you have an infinitesimally small slice that is df, then what is the width of that little df? I'm about to tell you, so if you want to think about it on your own and try to answer it, pause the video. But that little slice, the width of it, guess what, is dx, okay, is dx. And I'm going to call the distance from the origin to some arbitrary slice dx, I'm going to call that distance x, okay, distance x. So check out what I'm going to do here. I'm going to say the sum of the moments about point O on the original system is going to be equal to the integral from 0 to L of x times w as a function of x dx. All right? So let's take a second and we're looking only at the original system right now. I'm saying that if you take the integral of this x distance times w as a function of x, and you integrate that from 0 to L, you will end up getting the sum of the moments about point O in the original system. So what you're essentially doing is it's like you're taking this little slice times this distance x plus this little slice times another distance x, plus this little slice times this little distance x, infinitesimally from the origin to the total length. And you're adding them all up, okay? You're adding up these little differential slices times each of their own little moment arms, and you add them all up from 0 to L. And what do you end up getting? You end up getting a total moment about point O. Okay, so the book has a pretty much the same explanation, but probably some slightly better graphics than I'm drawing by hand in this video. So again, I can't emphasize enough. Read section 4.9 in the book to give you some more clarity if you're having trouble understanding what I'm saying here. Okay, so back on track. That's our sum of the moments about point O. In the original system, okay? Now, what about the total moment about point O, all right? M sub t about point O. So let's look in the equivalent system now. Well, in the equivalent system, that's pretty easy, right? We've just got capital F times x bar. And it's that simple, right? So we would say equals capital F times x bar. All right, and we set these equal to each other, right? So we say integral from 0 to L, x times w as a function of x dx equals f times x bar, okay? Now, remind me, what is f? We're going to say recall that f equals what? Integral from 0 to L of w as a function of x dx. We just had a couple of examples illustrating that. So what do we have now? We've got integral 0 to L x times w as a function of x dx equals integral from 0 to L w as a function of x dx times x bar. So that's what we have now. So what can we do? Can we cancel the integrals? No. Don't do that. You cannot cancel the integrals. You can't cancel anything inside of the integrals. You cannot cancel w as a function of x. You can't do any of that because they're both in integrals, okay? So what do? We rearrange and we solve for x bar. So we say x bar equals integral from 0 to L, x times w as a function of x dx divided by integral 0 to L, w as a function of x dx, okay? And this right here is our general formula to calculate x bar, all right? So you got to take two separate integrals. You cannot cancel anything. I know it looks tempting. It looks like you want to cancel the w as a function of x, or you want to try to cancel the integrals. You cannot do that. These terms are inside their own separate integrals. So there is no term cancellation at this stage of the process. So even though it looks tempting, do not do it. You will get the wrong answer. So this is our general x bar equation where we would have to evaluate two different integrals. Now, this process, if it feels a little familiar to you, it should. We did a process very similar to this, but with just point loads several examples ago. Okay, you had an example several examples ago where you were asked to, I'm actually flipping back in my notes to see if I can find the exact example we had a video on, but we had an example where, bear with me while I try to find it in my notes, where you were asked to find the distance away from like the left support of a beam, and you had a bunch of point loads acting all over that beam, and you had to find some distance d away from the left support. Okay, that was several videos back, but it was from content in chapter 4. Okay, so that process is pretty much the same thing that we're doing here. All right.